Let's look at the idea of work as a physicist would define it. To begin with, we need to think about the force, which we understand, and the distance we might apply that force through. Traditionally, we might use terms like x, maybe even d in the past for distance, but work usually uses the term s, the letter s, to define it. So if we move a box here, a distance s, and now we move the box to this position, we define the work as being the force times the distance. Since force is in units of newtons and distance is in units of meters in the SI system, work would have the units of Newton meters. Those hidden units, as we call them. A Newton would be a kilogram meter per second squared, mass times acceleration, multiplied by a mass. So a work of a Newton meter is going to be called a joule, and that will be a kilogram meter squared per second squared. So work is expressed in units of joules. The question then arises, well, what if the force is not along that direction? What if the force is along this direction, and this is your force? Well, the actual definition of work looks like this in vector terms. It says take the vector s and dot it into the distance. This dot right here in vector terminology doesn't mean multiply. It is something special called a dot product. What we need if we want to talk about moving this along a distance is this component of the force. That is the component in the direction of the distance we are moving in. But we know what that component is. If we have an angle here, theta, then this component is simply f times the cosine of theta, where f is the magnitude of the vector f. So this dot product then means to take f and multiply it by the cosine of the angle between f and s. So in this case, here is the force. We're moving it along this axis, a distance s. We take this angle theta, and we need this component of the force in this direction. So the work is equal to f times the cosine of theta multiplied by the distance. It is the force component in the direction of the distance. Mathematically, we have F equal F. It's called a dot. It doesn't mean multiply. It means the dot product, F dotted into S. And the actual definition would be to take F, multiply it by S, and then multiply it by the cosine between the vector F and the vector S. This would be the definition of the dot product. So if we have a box here and we move it along this direction and the force is in this direction, then the work is equal to Fs cosine of the angle between these two. But the angle is 0, and the cosine of 0 is equal to 1, so we get the work is equal simply to the force times the distance. And that's the equation we started with when we were thinking only in simple terms. What happens if the force is in this direction? Well, it isn't going to move it very far along here, but let's see what the equation looks like. The work is defined as F dotted into the distance. That means the force, the magnitude of the force, times the magnitude of the distance, not including the vector, times the cosine of the angle between the force and the displacement vector here, which would be S. Well, in this case, the angle here is 90 degrees. The cosine of 90 degrees is 0. So we would have F times S times 0, and we would get 0. And that's what we might expect, because if we pull up, we don't exert any force in the direction of this distance, so we would have no work. The work would equal to 0. But what happens if the direction of the force is arbitrary and the direction of S is arbitrary? So this would be our displacement S, and this would be F. The work is equal to the vector F dotted into the displacement S, which means take F, multiply by S, multiply the cosine of the angle between F and S. Here is the angle theta. And essentially what we are doing is getting the component of F that lies along S. If we write this as F cosine theta, then times S, we are just getting the component of F that lies along S. Now let us look at a practical example. Let this be our x-axis. Suppose we have an object that we would like to move along this x-axis a distance of 20 meters. Our force is in this direction, pulled up at an angle of 42 degrees, and our force is going to be 25 newtons. We look at the work, and it's equal to F dotted into S, which is equal to F times the cosine of the angle between F and S times S. So that's equal to 20 newtons times the cosine of 42 degrees times 20 meters. Equal 297, let's look at our units, Newton meters, which we know is equal to a joule. So our answer is 297 joules. Remember again that a joule is a kilogram meter squared per second squared. One final example. We want to move vertically. Let's say we're lifting a set of barbell weights of some kind, and we're going to pull them up a distance of 15 meters. The barbell itself would have a mass, let's say, of 50 kilograms. In order to calculate the work, we need the force dotted into the dot product. In this case, the force and the distance are along the same axis. So I have F times the cosine of theta times S. F, but this is the cosine of 0 degrees, since they're in the same time, S, and cosine of 0 degrees is equal to 1. So this is just equal to force times distance. What is our force? Well, if this is 50 kilograms as our mass, the force must be mg. That's pulling down, and we have to work against that. We multiply by that by the distance of 15 meters. So this would be 50 kilograms, 9.8 meters per second squared, 15 meters. And we see that we have 7350 joules of work. Kilogram meter squared per second squared. As a final note, the correct number of significant figures is really only 2, so we would say our answer is 7,400 joules.